In the late 1600s, there was a grand debate between two giants of physics, Isaac Newton and Christian Huygens. Isaac Newton believed that light was a stream of particles, while Huygens believed that it was a wave. In 1801, Thomas Young decided to settle the debate with a double slit experiment. He shined light through two narrow slits, and whatever light passed through would project on a screen. How does this help us find out if light is made of particles or waves? Well, if it were made of particles, you'd imagine two bands on the screen corresponding with the two slits. However, if it were a wave, new waves would propagate from the slits and they'd interact, interfering with each other. Amplitudes would add, canceling some waves out and making others stronger. And guess what? Every time the experiment is run, we always get this interference effect. So boom, light is a wave, right? Not so fast. In the early 1900s, physicists were aware of something called the photoelectric effect, where certain types of light would knock electrons out of certain metals. Incidentally, this is how solar panels work. One would imagine that the more intense the light was, or how much light there would be concentrated, the more electrons would come out, right? Wrong. In experiments, it was found that the amount of electrons which are knocked out of metal does not depend on the intensity, but the frequency of the light. What? In 1905, an unknown physicist named Albert Einstein, wonder who that is, postulated that the only possible solution would be if light came in quantized chunks, particles whose energy depended on frequency. That way, intensity wouldn't matter because you'd only have one particle of light, or photon, hitting an electron at a time anyway. This added to a growing pool of evidence that light was made of particles. So, how in the world can something show properties of being a wave and a particle? And keep in mind, these are just two examples amongst thousands of experiments which prove one way or the other. Let's return to slits to add some more peculiarity to the mix. Imagine I added one photon into the double slit experiment at a time. Scientists have done this, and guess what? There's an interference pattern. But what in the world is the photon interfering with? And finally, just to add to the chaos, observe this great experiment done by the YouTuber Veritasium. He's shining a laser through a slit, which is making narrower. As you can see, it gets smaller and smaller, but at a certain point, it gets bigger. How does that make any sense? What is going on? If you've ever studied physics, this should go against everything you've ever known. In classical mechanics, all you need to know to calculate anything about a particle is its position and its momentum. Clearly, that can no longer be trusted. In experiments like the photoelectric effect, where the momentum of the light is unclear, it manifests itself in particles with definite position. In contrast, in the double slit experiment, we have a pretty good idea of the momentum of the light, and so it spreads out, giving us an undefinite position. It seems like there's a relationship between how uncertain we are in the momentum of something and the position of something. This is expressed in Heisenberg's uncertainty principle, which states that the sum of the uncertainties in position and momentum cannot be less than a small number. Hence, if the uncertainty in position goes up, uncertainty in momentum must go down, and vice versa. It is because the number on the right is so small that quantum mechanics and its uncertainties don't apply as much to larger objects. So, how do we predict motion? It's inherent that quantum mechanics is undeterministic, and that we can only rely on the probabilities of a particle being at a certain position. Thus, we derive the wave function, which is approximately defined as the square of the probability of something being in a certain position. Sometimes the graph is hyperlocalized, and other times it's more like a plane wave. However, this does give us something quantitative to work with. It is based off of this that we derive the Schrödinger equation, the dynamics equation of quantum mechanics, the F equals ma of microscopic particles. I know it's a lot of weird symbols, but all it is saying is that the change over time in the wave function is equal to the Hamiltonian of the particle, which is a fancy number physicists use, which basically means the sum of all the energy of the particle. It's in this way that physicists can calculate how the wave function changes over time, which gives us a feel for the position and the momentum. These are the foundations of quantum mechanics. Trust me, it only gets weirder from this point on. It's a miracle of human ingenuity that we are able to decipher the quantum world. The only question is, what will we discover next?